Welcome to This Explainer. I'm absolutely thrilled you're joining me today. We're going to put on our digital detective hats right out of the gate because we're conducting a forensic investigation into a massive, hidden architectural failure happening right beneath our screens. Honestly, by the end of this, we're going to fundamentally challenge how you think about the math running our entire digital economy and the very foundation of verifiable truth.
Get this. It's a staggering fact that between 80 to 90% of modern AI compute cycles, they aren't exact math. They're actually just hardware-level approximations. That's right. When massive language models and high-speed algorithms are doing all that heavy lifting, they literally aren't calculating exact ground truth realities. They're fundamentally making highly educated guesses just to keep up with the absolute fire hose of data.
So to really dive into this, we actually need to start by completely shattering a core myth. We all kind of love to assume computers are these perfect, flawless math machines, right? Dealing only in absolute, rigorous logic. But the truth, hiding way down at the microscopic level of the silicon, is that they're fundamentally estimation systems. In the pursuit of blistering speed, our multi-thousand-dollar advanced machines are, quite literally, forced to guess.
Okay, so here's our roadmap for this explainer. First, we'll look at the grand computational illusion. Then we'll meet the FPU gambler, hit the trig wall, explore the wood chipper effect, and wrap up with the exact ALU surveyor. Let's get into it.
Part 1. The grand computational illusion. Infinite reality versus discrete machines. To truly wrap our heads around this crisis, we have to look at the massive friction between our continuous, infinite physical reality and the rigid, discrete nature of a digital machine. Think about the 1 over the square root of 2 quantum state. Now, this represents a perfect, continuous superposition, an infinite, smooth physical reality. The mathematical substrate of our physical universe is absolute, and it's perfect. It flows continuously, a lot like fluid vector spaces or even human associative thought. There are no jagged edges in reality.
But here's the absolute critical question. How exactly does a rigid discrete computer process that infinite continuous reality? Well, it struggles. Digital computers operate on this relentless, unyielding mechanical grid of timed execution cycles. Ones and zeros, high and low voltages. They simply cannot handle smooth, continuous concepts natively. This modality mismatch between an infinite reality and a strict, finite digital grid is exactly where the illusion of perfect computing completely breaks down.
Which brings us to Section 2. Meet the FPU gambler, the hardware flaw. Let's shrink all the way down to the microscopic silicon level to meet the primary antagonist responsible for processing all these continuous numbers inside your machine.
Deep inside a computer's physical brain, there are actually two radically different ways to process reality. On one side, we have the floating point unit, or as we're calling it, the FPU gambler. Now, it's incredibly fast, sure, but it's probabilistic and lossy. To achieve that blistering speed, chip manufacturers literally burn their own completely secret, proprietary mathematical seed tables directly into the physical silicon just to help it guess the answer. On the flip side, we have the arithmetic logic unit, the ALU surveyor. The surveyor is slower, yeah, but it deals strictly in exact, universally deterministic hardware truths. 1 + 1 = exactly 2 every single time, on every machine on Earth. But right now, modern systems are heavily relying on that wildly guessing gambler.
So here's the real kicker. How does this gambler actually behave when faced with infinity? When the FPU is tasked with calculating that perfect, continuous superposition we talked about, the sheer observer complexity completely exceeds its physical memory bounds. There's just not enough space. So it's forced into what experts call systematic contraction bias. To handle infinite rational precision, the hardware collapses that perfection into rounded, standardized, fixed bins. It literally chops off tiny microscopic fractions, standardized across the industry as the 23rd bit chop. It's literally throwing away decimal places. And doing this irreversibly erases information, creating this invisible, snowballing layer of what the source material calls observer debt.
Just think about the sheer, overwhelming volume of continuous data here. It practically forces the hardware into these lossy, switchback estimations just to survive. It's kind of like trying to fit an infinitely detailed, massive Renaissance painting into a tiny, low-resolution digital picture frame. The nuance gets completely lost as the hardware frantically cuts corners just to keep up with the flow of data. Let's move on to Section 3. Hitting the trig wall, the friction of curves. Let's see exactly what happens when algorithms force continuous geometry through these fixed, discrete bits.
Think about how AI or advanced financial systems try to map meaning.
They use complex geometric graphs, right? Relying heavily on continuous curves and angles. Heavy trigonometry, calculating things like sine or cosine. But remember, the computer hardware is fundamentally made of rigid, discrete squares. When you force continuous curves into those rigid grids, you create absolutely devastating friction. You're forcing the FPU gambler to guess how to fit a round peg into a square hole. And the more complex the curve, the more the FPU has to guess. These approximation errors compound rapidly until they hit a critical failure line that researchers literally call hitting the Trig wall. It is an absolute plague of hardware non-determinism.
That escalates us right into Section 4, the wood chipper effect, the destruction of provenance. It's time to take our autopsy from these microscopic silicon flaws up to the macroscopic disasters they create in the real world. Okay, so when we rely on the guessing FPU gambler, we trigger this wood chipper effect. Let's walk through it chronologically. Step 1. Your system ingests exact, verifiable source data. Maybe it's a financial ledger or a copyrighted book. Step 2. The FPU hardware approximates the math using those completely secret corporate seed tables burned right into the silicon. And then step 3, because that math was fundamentally a guess and not a precise trackable calculation, the original data provenance, your actual chain of title, is permanently lost. Gone. The sources use a fantastic metaphor here. The FPU acts like a giant blender. You know exactly what fruits you tossed in at the start, but because the hardware chopped off tiny fractions and approximated all the math, you absolutely cannot reverse engineer that smoothie back into the exact original fruits it came from. The liquidation of contributors and data provenance is a completely one-way street. You simply cannot build verifiable digital trust on a foundation that is fundamentally just guessing.
But hey, it's not all doom and gloom. Welcome to Section 5, the exact ALU surveyor, restoring verifiable trust. Let's finally meet the hero of our story, who's been sitting quietly inside our computers this entire time.
Let's look at the ultimate solution here, bypassing the gambler entirely. Instead of fighting the hardware, we can actually speak its native geometric language. By shifting our math away from continuous curves and into discrete, exact integer rings, using centuries-old math tricks like Pell's equation to perfectly map curves onto a strict pixelated grid, we completely remove the need for decimals. This allows the strictly deterministic ALU surveyor to take over operations. And because the surveyor flat-out refuses to guess, it restores absolute, globally accountable mathematical receipts. Boom.
And that brings us to this incredibly powerful insight from the source material. It says, authorship is not a vibe, it is a bit-perfect causal chain anchored in biological labor. Wow. That perfectly encapsulates why the ALU's exactness is so absolutely critical. If we actually want to protect human intent, intellectual property, and our financial ledgers, we need uncompromising mathematical truth. We need a bit-perfect, deterministic witness to our actions, not a rough estimation.
As we continue to offload our finances, our legal frameworks, and our medical systems onto machines, I really want to leave you with this final thought to deeply ponder. In the future of high-stakes computing, what standard of accountability are you willing to accept? Are you going to settle for the gambler's wildly fast but lossy guess, letting invisible hardware passively blur the lines of absolute truth? Or will you demand the surveyor's perfectly traceable blueprint? Keep asking the hard questions about the systems you rely on every single day. Thank you so much for joining me on this explainer, and keep learning.